Okay guys, for today's installment, lectures helping you guys prep for standardized exams, I want to help refresh in your minds this topic of substitution and elimination reactions. By the end of this lecture, you guys should be able to do the following. Know the mechanistic differences between SN1, 2, E1, and E2 reactions. Be able to identify particular reaction conditions as SN1, 2, E1, or E2. Recognize that dehydrations are really just elimination reactions of water. And know that for E2 reactions, a leaving group and eliminated hydrogen must be anti-paraplanar. Be able to identify the elimination products in straight chain and six-member rings of such reactions. Let's go ahead and get started. To remind you guys, substitution reactions look like this. A leaving group, shown here as a bromine, is attacked by a nucleophile, which comes in and kicks off the bromine and replaces it. We can say then that the OH has taken the place of the bromine in this reaction, or is substituted itself for the bromine. In contrast, an elimination reaction looks like this. Instead of a nucleophile coming in and replacing the bromine, it instead grabs a hydrogen that's on the carbon adjacent to the bromine. The hydrogen then gets removed. The electrons close down like a trapdoor, kick off the leaving group to give an alkene. Now I should point out that an elimination reaction doesn't always have to involve bromine, neither does a substitution. It just involves some good leaving group. So bromine is shown here in this example. Now we'll first be addressing substitution reactions in detail. Then we'll get on to elimination reactions. There are two different kinds of substitution reactions, SN1s and SN2s. I'll first review the mechanism of the SN1 reaction. First, a molecule like this, which has a good leaving group on it, is heated up and the leaving group takes off to generate this high-energy carbocation intermediate. At this stage, a nucleophile comes in, forms a bond with that carbon, and forms these products here in which the nucleophile has substituted itself for where the leaving group was. Now there are two things you need to remember. The slow or rate determining step of this whole reaction is the first step, the formation of the carbocation intermediate. I cannot emphasize to you guys strongly enough how important it is to understand that. The reason that an SN1 reaction is an SN1 reaction is because the slow step only involves one molecule, this starting material. What that means is you could increase the concentration of the nucleophile as much as you wanted and it would not increase the rate of this reaction. Only increasing the concentration of this one molecule, the rate determining molecule, will change the rate of the reaction. The other thing I want you to remember is that because the nucleophile can attack this carbocation right here from either side, front or back, SN1 reactions give a mixture of enantiomers in the product. Now for the mechanism of the SN2 reaction. First, we have our starting material, but this time instead of the leaving group taking off, what occurs is a strong nucleophile comes in and in one step kicks the leaving group off. Now because this occurs in a single step, the leaving group getting kicked off at the same time that the nucleophile is coming in, the nucleophile has to come in from the rear. Comes in from the rear side opposite the leaving group, and thus we get an inversion of stereochemistry. Two nuances. First, the slow rate determining step of this happens to be the only step. This nucleophile coming in and kicking off the leaving group. Thus, there are two molecules that determine the rate of this reaction, both the nucleophile and this starting material. Altering the concentration of either of these two participants will alter the rate of this reaction. Nuance 2, because the nucleophile can only attack from the backside relative to this leaving group, SN2 reactions give the inverted relative enantiomer as the sole product. That is in contrast with an SN1 reaction. As I mentioned before, the slow step in the SN1 reaction is the formation of the carbocation intermediate. The speed of this slow step will be increased if the carbocation formed is more stable. So you see these different types of carbocations we could possibly get, or molecules I should say, that could form carbocations. You'll notice that a primary carbon, if the leaving group took off, it would give me a primary carbocation. that is extremely unstable. It's so unstable, in fact, that SN1s cannot, or I should say primary carbon-leaving groups, cannot do SN1 or E1 reactions. Secondary carbons can, tertiaries are great, and then allylic carbons are even better because this carbon, or the carbocation that would form here, is stabilized by resonance into the double bond. This, although this might look like a primary carbocation if I took the leaving group off, it is not. It is an allyl carbocation. That's a carbocation that's stabilized by resonance into this allyl group. This is even more stable than a tertiary carbocation. And the most stable in this group would be a benzylic carbocation. If this leaving group took off, this positive charge would be stabilized by resonance through this entire ring. Alright, now SN2 reactions do not form carbocation intermediates. Instead, the nucleophile does backside attack directly on the carbon that's stuck to the leaving group. As a result, the trend for SN2s is the opposite. A primary carbocation is much, much better at doing an SN2. Much, much better. Because a nucleophile can come in more easily and kick off a leaving group on a primary carbocation than it can on a secondary. Secondary has more real estate in the way, more steric interference with these groups. It's harder to get in here because there's two groups in the way. And over here, a tertiary carbon cannot undergo SN2, so I can't have a nucleophile come in and into a tertiary carbon kick off the leaving group. It's just too sterically hindered. So if I run an SN2 style reaction and I have a tertiary carbon, the nucleophile will not do an SN2. Instead, it will probably do an E2. Now we move on to elimination reactions. As with substitutions, there are two different kinds of elimination reactions, E1 and E2. Here's the mechanism of the E1 reaction. Once again, I have a molecule that looks very similar to my SN1 reaction starting material. Leaving group takes off, giving me a carbocation intermediate. At this stage, my base comes in and grabs a hydrogen off the carbon adjacent to it, dumps the electrons down, close like a trapdoor, giving me an alkene product. That's the mechanism of the E1 reaction. Now, one thing I want you to know is that the slow or rate determining step of the E1 reaction is also the formation of the carbocation intermediate, just like with an SN1. Thus, altering the concentration of the base does not change the rate of this reaction. The rate is determined by one molecule, this starting material right here. Here's the mechanism for an E2 reaction. In this circumstance, I have my leaving group right here, and my base comes in, and in a single step, tears a hydrogen off, dumps the electrons down, and kicks the leaving group off, all in one step. Ba-bam! Here's my product, the alkene. You'll notice that there's no carbocation generated in the mechanism for an E2 reaction. Thus, the slow step is the only step, and it is determined by the concentrations of both the base and the starting material molecule. So altering the concentrations of either of these will alter the rate of the reaction. That is why we have the number 2 in an E2 reaction. Now, as you guys should remember, elimination reactions, both E1 and E2, generally favor the more substituted alkenes. This is called Zaitsev's rule. So you could see that in this example up here, I could imagine doing an elimination on the left side to give this product, or in the middle to give this internal alkene. The internal alkene is the major product, the one favored, because it's more substituted. Similarly, if I do an elimination of this product right here, I could imagine doing it on the external position to give me this alkene, or the internal position to give me the more substituted alkene. Once again, because of Zaitsev's rule, the more substituted alkene is the one that is favored. Elimination reactions also usually favor the alkene that has the bulkiest groups on the opposite sides of each other, which is typically the E-alkene. So you can see if I did an elimination on this, I could get two potential products theoretically. One has this tert-butyl group on the same side as the methyl, and the other has the tert-butyl group on the opposite side of the methyl, the E isomer. The E isomer is the major product, once again, because that happens to be more stable. Now you might remember from before that SN2 reactions work best when the leaving groups are attached to primary or secondary carbons. Now you remember, an SN2 reaction is where the nucleophile comes in a single step, ba-bam, and kicks off the leaving group. There's no carbocation generated. Thus, a primary carbon is much easier to be attacked than a secondary. So SN2s prefer primaries over secondaries. They don't work at all on tertiary carbons because a nucleophile can't get in to this carbon center to substitute. Now this is not true for E2 reactions. Because E2 reactions favor the more substituted product according to Zaitsev's rule, they also react best when leaving groups are attached to tertiary carbons, followed by secondary, followed by primary. So E2 reactions, oddly enough, do prefer tertiary over secondary over primary. SN2s are the only guys who are the opposite. They prefer primary over secondary over tertiary. I hope that makes sense. Now one more nuance. In general, having a better or more reactive leaving group will increase the speed of any substitution or elimination reaction, as you can see here. Better leaving groups make for better substitution or elimination reactions. The ever-confusing question we face is whether a particular reaction will do an SN1, E1, SN2, or E2 reaction. That, of course, depends upon the conditions and the identity of the starting material. I'm going to give you guys 3 sequential questions you can ask yourselves to answer this question. That is, to help you determine whether or not a particular reaction will do SN1, E1, SN2, or E2. Now, I should warn you that this series of questions is not 100% foolproof. For some specific real-life circumstances, the answers you might come up with doing Mike's series of questions here might actually be wrong. However, I think they're generally pretty accurate to help guide you for these types of problems that you might encounter on standardized exams. So here we go. Question number 1. Is the carbon bonded to my leaving group primary, secondary, or tertiary? If it's primary, then the reaction is SN2 or E2. If tertiary, then the reaction is SN1, E1, or E2. And if secondary, or a stabilized carbocation, such as an allyl or benzyl carbocation, then it can be any of the above. So here are some examples here. SN2 or E2, primary carbon, SN1, E1, or E2, tertiary carbon, and stabilized could potentially be any of the above. So we ask ourselves this first question, get the answer, and eliminate some stuff, and then we go on to the next question. Here is that next question. Is my nucleophile or base strong or weak? Now I'm going to tell you guys how to distinguish between the two. A strong nucleophile or base generally has a negative charge. Now there's some exceptions to this. Negative charges on halogens or negative charges that are resonance stabilized are weak. If your nucleophile/base is strong, then your reaction is a 2 reaction. If it's weak, then your reaction is a 1 reaction. So here's the reason why this question is so crucial. If you have a strong nucleophile/base, it's very, very reactive. You've got a localized negative charge sitting on a reactive atom. It is not going to sit around and wait for a leaving group to take off to form a carbocation. It's just going to go ba-bam and react with your molecule, SN2 or E2 style. If you've got a weak Humpty Dumpty style nucleophile/base, it will wait around long enough for a leaving group to take off, SN1 or E1. Does that make sense? If your nucleophile/base is strong, it'll be a 2 reaction. If it's weak, it'll be a 1 reaction. Here are some examples of those. Strong nucleophile/bases are any metal stuck, and this M represents a metal, to any of these kinds of guys. Weak nukes or bases are resonance stabilized nucleophiles, or guys who just have lone pairs. They don't have negative charges at all. Or negative charges on halogens. Halogens are very stable with negative charges, so they aren't reactive enough to favor SN2 or E2. Next question. Is my nucleophile/base a nucleophile or a base? In substitution and elimination reactions, a nucleophile is technically something that does a substitution, while a base is something that does elimination. Larger nucleophile/bases tend to behave more as bases, that is, they do elimination, because they can't fit as easily into a carbon bonded to a leaving group to do a substitution. They therefore prefer to tear off a hydrogen next door to do an elimination. For this class, and probably for most of your standardized exams, any nucleophile/base that looks larger than ethanol when you draw it on paper is a base, and we'll do an E reaction. Anything smaller is a nucleophile, and we'll do an S reaction. Now, there are exceptions. Although acetate, this molecule right here, looks bigger than ethanol on paper, it is a nucleophile, and we'll do S reactions. Also, negatively charged carbon and sulfur atoms are usually nucleophile no matter how big they are. So here's some example. Nucleophiles smaller than ethanol on paper, these kinds of guys. Bases bigger than ethanol on paper, these kinds of guys, where R is ethyl or larger. I hope that makes sense. Here's some examples that I've come up with myself. We'll go through the line of questions. Question number 1, is my leaving group stuck to a primary, secondary, or tertiary carbon? Now, this particular carbon is a secondary, and not only is it a secondary, but it's also a stabilized secondary carbon into this benzyl group. So that tells me that this reaction could be any of the above, SN1, SN2, E1, or E2. Next question, is my nucleophile/base strong or weak? Now remember, anytime we see a metal like potassium, sodium, or lithium, we just think of it as being a negative charge. So this is an OH with a minus charge on the oxygen. That is a strong nucleophile/base. Since it's strong, we know that this is a 2 reaction. So I can cross off SN1 and E1. This has to be an SN2 or E2 reaction. The next question, is my nucleophile/base a nucleophile or a base? On paper, this molecule is smaller than ethanol, so it's a nuke. That means it's going to prefer an SN2. So my product is going to be an SN2 reaction, even though for some reason I've shown an E2 product here. Dang it to heck. Let's go ahead and look at another example here. Here's an example. I go look at my leaving group. Is it stuck to primary, secondary, or tertiary carbon? It's secondary. So which of the reactions could it be? Any of the above. I go to my next question. Is my nucleophile/base strong or weak? It's weak. This is an oxygen that does not have a negative charge. It's not stuck to potassium, sodium, or lithium. All it has is lone pairs. It is weak. So what does that tell me? It tells me that the reaction is a 1 reaction, either E1 or SN1. Next question. Is my nucleophile/base a nucleophile or base? Well, this is smaller than ethanol, so it's a nuke. That tells me that it's going to be an SN1. Also, heat generally indicates that you've got an SN1 or E1. So let's see what our SN1 product looks like. There it is. Now here are some other examples that I've shown. I'm not going to give you the answers, but I invite you to scroll through them and see if you can figure out the answers on your own. Here are some other examples that I won't attempt here, but I'll invite you guys to try them on your own. And here are some more as well. Can you tell me if it's SN1, E1, SN2, or E2? Now there's one other additional nuance that you should remember. Because the E1 reactions, because E1 reactions form carbocation intermediates, carbocation rearrangements such as 1,2-hydride and 1,2-methyl shifts are possible. There is an example. I've got a bromine that can take off, giving me a carbocation here. This carbocation is a secondary carbocation. If this hydride next door shifts, fills in that hole, and leaves a carbocation here, this is a secondary allylic carbocation. This is much more stable, so a 1,2-hydride shift will occur, and ultimately the elimination reaction here will give me this product, as opposed to the product that would be given if I only eliminated out here or in the middle here. Does that make sense? Here's another example. Chloride takes off, carbocation secondary. I can have a methyl move over. Now I get a tertiary benzylic carbocation, much more stable. The elimination then occurs to give me this product. What's the take-home from the slide? Here's the take-home. If you're doing an E1 or an SN1 reaction, you form a carbocation. If a 1,2-hydride shift or 1,2-methyl shift can occur to generate an intermediate that's more stable carbocation, then it will. And then the product that you get will be from the more stable carbocation instead. Now here's something else I want you to know. As it turns out, if you do an elimination of an OH, that type of elimination is called a dehydration. I don't know why, but we give it that special name. Ultimately, we're removing H2O. So you're taking away an OH and an H next door. You add an H to an OH, that ultimately is H2O. So we're removing water. So anytime we do an elimination of OH, it really is often referred to as a dehydration. That's all an elimination of an OH is. It's a dehydration. A dehydration is an elimination of an OH and vice versa. In effect, it is an elimination of water. This reaction is catalyzed by H2SO4 and heat. So now we're going to look at some questions. Once again, I won't answer them for you, but I'll invite you to look at them and see if you can come up with the answers. Question number 1. The rate of an SN1 reaction is first order because of which of the following? Question number 2. Which of the following will do an SN1 reaction most quickly? Question number 3. What is the rate limiting step of the SN1 reaction shown below? So here's the mechanism. Which one is the rate determining step? Next question. What is the product of the following reaction? Ooh, this is a subtle one. Let's see if you can figure it out. Which of the following will do an SN1 reaction most quickly? Kind of like our other question, except these molecules are slightly different, and they do require you to think about the mechanism in order to predict the correct answer. And then this question, what is the major product of the reaction shown here to the right? What is the major product there? I'll give you a hint. Some of these questions involve hydride or methyl shifts, so make sure you take a look at that. Alright, now to some other subtleties. In order for an E2 reaction to work, the bonds that are eliminated, that is this H group and this X group, have to be in the same plane. That is, they have to have an eclipsed they can't have an eclipsed conformation shown here. They have to have this staggered anti-paraplanar conformation in order to work. So syn elimination shown here doesn't really work. Anti-elimination does. So once again, the leaving group and the H that's being removed have to be anti-paraplanar to each other. I hope that makes sense. Here's another way of looking at that. If I'm trying to do an elimination here, where this hydrogen and this X are eclipsed to each other, it does not work. Instead, I have to rotate around this bond so that they're anti-paraplanar to each other, staggered. And now I can do an E2 elimination. Okay? Alright. Now with that in mind, can you answer the following question? I want you to predict the major products of the following E2 reactions showing the correct easy stereochemistry. Now here's the deal. The hydrogen in each of these examples, there's only one hydrogen on the carbon adjacent to the leaving group. So I guarantee that that makes a difference. Make sure that you pay attention to this so that you can predict the correct answer. Now this anti-paraplanar necessity brings a few subtleties with it in cyclohexyl rings like this. As it turns out, in a ring of this type, you also have to have the H and the leaving group that are doing the elimination reaction be anti-paraplanar to each other. So let's take a look at this example. I've got my leaving group right here. It's equatorial. If a leaving group is equatorial, it cannot do an elimination because there's no hydrogen that's anti-paraplanar to it. Instead, what has to occur is this ring has to do a ring flip so that the leaving group is axial. Now I've got an axial anti-paraplanar hydrogen that can be eliminated. Now keep in mind this only applies to E2 eliminations. In E1 eliminations, it doesn't matter if the H or X are anti-paraplanar because there's a carbocation intermediate formed. So in E1 reactions, the leaving group takes off and gives me a carbocation. Now there's no such thing as anti-paraplanar. Carbocation, I can fill that hole however I want. So this H does not have to be anti-paraplanar to the leaving group if I do E1 conditions. I can do them nice and neat. So that ends our review of elimination substitution reactions. I hope it's been fun for you guys. I've had a blast. I promise you I'm going to give you all these questions to practice in class, and hopefully you can review and remind your minds of something that you should Hoop-a-pop-a-doop-a-doop. Deedly-doo. So let's have a good day. I don't know what else to say. I've got to take a nap. All right. Bye.